I am about to tell you the secret to predicting all periodic trends. If there's one thing you walk away from this chapter, I really want you to walk away with this. And as long as you practice, so don't just memorize this, also do active recall. Practice applying it to periodic trends, atomic radius, ionic radius, ionization energy, so on and so forth. But the key to predicting periodic trends is actually the electrostatic interaction energy. So all periodic trends can be predicted using the energy of electrostatic interaction. E electrostatic is proportional to Q1 times Q2 divided by the distance d between them. And yes, I want you to have this memorized. I told you to memorize it a couple of weeks ago, so hopefully you already have this down, but if not, here's your chance to catch up. So let's take a look at atomic radius as an example. So here Q1 will be the charge on our nucleus, Q2 will be the charge on our electron, d is the distance between them, and let's start, for the sake of simplicity, with lithium. So in lithium's case, we have 3 protons in the nucleus, so a +3 charge for Q1. Q2 will be just 1 electron that we're worried about being attracted to it. And specifically, we're looking at the valence electron. So this is our 2s electron. The electrons, there are 2 of them, the electrons in 1s are what we call core electrons. So they are below the valence shell. Valence shell is our outermost electron, outermost energy shell, so here N of 2. And we're worried about what the outermost electrons feel in terms of their attraction to that center. So let's not even worry about distance right now, and let's compare this to beryllium. So in the case of beryllium, we have a +4 charge. Again, we're considering 1 valence electron, so -1. And again, let's just assume that the distances are completely comparable initially. And when we do this, we see that the electrostatic energy of interaction is going to be stronger in beryllium because of the higher nuclear charge. And so what this means is, because there's a higher energy of interaction, that energy is actually going to end up pulling the valence electrons in. And so that distance is actually going to end up being slightly smaller. And so beryllium actually has a smaller radius, atomic radius, than lithium does. Now let's compare lithium to sodium. Now, in the case of sodium, so if you consider your periodic table, we have hydrogen, lithium, then sodium going down in our periods. And so sodium adds an entire energy shell. We go up to N of 3. Lithium goes up to N of 2. Sodium goes up to N of 3. And adding that entire extra energy shell literally adds radius. It adds distance. In addition, I mentioned valence and core electrons before. So here we have more core electrons, which are then going to increase the number of electron-electron repulsions. So it's simple just to think of adding a shell, think of adding layers on like an onion. You're going to increase your radius. You're also going to increase repulsion. So now let's consider lithium versus sodium. So as we go down the periodic table on the alkali metals, we have hydrogen first, then lithium, then in period 3 we have sodium. So we've added a whole extra energy shell. And I've given some coloration in this image here. I have the 1s is all in red. So the N equals 1 shell is all in red. The N equals 2 shell is in orange. And now it's the N of 3 that's in yellow. So that's our valence shell in the yellow. And so if we consider lithium, we already looked at the attraction before. We have a +3 on the nucleus and a -1 on our valence electron. And when we look at repulsion, now I'm considering the 2 core electrons versus my 1 valence electron. And you'll notice that for distance, I have d minus y. In a moment on the next slide, you'll see that we can even ignore that. But all I'm doing is acknowledging that the distance between our electrons is slightly less than the distance between our valence electron and our nucleus. Now, if we consider sodium, in the case of sodium, we see that we have 10 nuclear protons. Boom! Now, in the case of sodium, we see that the nucleus has a +10 charge. So that's way more attraction, right? But then if you look at the very next term, you see we also have way more repulsion. So what we're going to do is we're going to plug in these numbers, and similar to before, we're even going to ignore distance for a moment. Let's just focus on what's going on in the numerator. And if we compare the strengths of repulsion, we can see that the repulsion in lithium is in fact much less than the repulsion in sodium. And so what this tells us then is that the electrons in sodium are going to repel each other, which means they're going to force each other farther away. And so we can predict that the atomic radius in sodium will be larger than that in lithium. So let's review what we just went through. So if we consider lithium versus beryllium, we said that the increased charge on beryllium in its nucleus compared to the charge of lithium is going to pull those valence electrons closer. And as you can see on the diagram here, that as we go from lithium to beryllium, the radius does in fact shrink. And it's true that as a trend from left to right, atomic radius decreases. Now, as we go down the periodic table, we can see that atomic radius increases. And if we think about lithium versus sodium, it makes sense because even though sodium does have an increased charge, it also has way more core electrons. And those core electrons are going to repel and force our valence electrons slightly further out. Another simpler way of thinking about this is just to think that we're adding an energy shell. So every shell is slightly larger in radius.